Hey, so let's continue with going over the Chapter 2 study guide answers. We just did A and B, or I did A and B the other day, and we're going to look at learning outcome C and D. So learning outcome C is explain the meaning of the terms producer, consumer, predator, prey, and trophic level in context of food chains and food webs. Those questions are going to be 1, 2, 3, 4, 6, 7, 10, 11, 12, and 40. And then learning outcome D is explain how populations of predator and prey may be interrelated. And that's going to be numbers 9, 13, 38, 48, 50, 51, 52, 53, 54, 55, 56, 57. Okay, so number 1, with reference. So that's the biggest thing is we have to then do what they say and reference the food web or the food chain or whatever they're telling you to reference. Explain, so we're going to need a definition and we're going to need an example. What is meant by the term producer? So we're definitely talking about its role. This question also will be more easily answered, I think, after Chapter 3, where we specifically talk about producers and energy. So a producer is, it's going to create or synthesize its own organic material. Or you could say it creates organic material for consumers or for organisms in the food web. They do this by photosynthesis. We know that because it's kelp. Kelp is green. Don't say they make food. You'd want to say they make organic material or chemical energy. Reference that they use sunlight. They create glucose, or they create a carbohydrate, or you could put C6H12O6. They do this by taking in water and oxygen, and I'm like disgusted I just said that. They take in water and carbon dioxide, and they release oxygen, and then we need to reference that kelp is a producer. 2, what's the energy source for this hydrothermal vent community? It's always hydrogen sulfide, H2S. 3, which organisms are the producers? Well, they're the ones taking in your energy source, your hydrogen sulfide energy source. The things taking in an energy source, if this said sunlight, and you never put sunlight on a food web, but if this was sunlight, you would know that your photosynthesizers were the ones taking in sunlight. So the producers are going to be the ones that are taking in from the energy source, which is hydrogen sulfide. So it's going to be mutualistic bacteria, also vent bacteria. And that should have another one on there. It should also say vent bacteria because it is organisms. Zooplankton feed on vent bacteria, and the zooplankton are eaten by galloping crabs. The crabs are then eaten by a ratfish. So vent bacteria gets eaten by zooplankton. Zooplankton gets eaten by the crabs. And then the crab gets eaten by the ratfish. Add this information to 2.2. I did not, we need to have another thing on here. It needs to also say crabs. Let me pause it and I'll show you what it's going to look like. Okay. Make myself bigger here. And make myself backwards. Okay. This is backwards for me. So I added it in on the top. Zooplankton gets eaten by the crab, and then the crab is eaten by the ratfish. It's 2 marks. The marks for this are your arrows pointing in the right direction. So they need to show the direction of energy transfer. So where your biomass is going. And the other mark is are they in the right order? So are they feeding off each other the right way? And then I also added the vent bacteria to that answer too. Okay. I'm going to unbackwards myself. Here I am. And I'm going to not make myself so big. There. All right. So that was 3. What are we doing after 3? 4? Okay, I just did 4. 5 is done. We're looking at 6. Okay. With reference, show the trophic levels. So our ice algae, sometimes this one is weird because algae is not on the outside or at the bottom like we're used to seeing, but you don't see it taking in anything, plus it's algae, but you don't see it taking in anything. We never put the sun in here. And that's because it's the creator, it's the originator. So Ice algae is going to be one of our producers. The other producers, phytoplankton, and ice algae is in trophic level 1. The Antarctic silverfish. So ice algae gets eaten by krill, which puts the krill at trophic level 2. It's a primary consumer. And then your silverfish eats the krill, and so that's going to be a secondary consumer or your third trophic level. 6, 7. We need to make a pyramid of energy. So easy, so easy. It's sketching, so you don't have to use a ruler. And you get 3 marks. If you can't fit the words inside the box, it's okay to write them on the outside. They don't look like a pyramid. That's not what it is. It is like stacked rectangles. So the 3 marks, that you need to have 5 stacked with decreasing magnitude, so they get smaller as you move up. Your biggest energy source has to be the phytoplankton because they're supporting everything above it. Nothing can have more than that. They need to be labeled. And if you can't fit it inside the box, you can write it on the outside. That's fine. And they need to be stacked centrally, not like off to the left or off to the right, stacked in the center. So easy marks to get for that. After 7, we have number 10. Same thing. Do a pyramid of energy for this food chain. Kelp, snails, crabs, octopuses, and sea otters. It is octopuses, not octopi. Again, it's stacked centrally with decreasing magnitude, and they're labeled. This one only is graded with 2 marks. 3 is really generous because it's so easy. 3 could also be a graph sometimes, but this one's only worth 2. So stacked centrally, again, it's not a pyramid. They need to be labeled, and you label on the outside if you don't have enough room. All right, and 11, using an example from 2.1, explain what is meant by. So what is meant by means using an example, and it means have a definition. The term trophic level. So this is part of your chapter 2 notes. Trophic means like feeder or nutrient. So trophic level literally means like your feeding position or your feeding level in a food chain or a food web. It's not who eats who. It's also not energy level. Energy level, when I read energy level, I think about Pokemon, honestly. It's embarrassing. But I also think about like your orbitals from your like atoms, like your atomic orbitals in chemistry. Those are different energy levels. That like 1s to 2sp, I don't remember what they are. That's okay. But that's what, if you're saying energy level, then you're talking like on an atomic level, and that's not this class. So don't say energy level. It also it tells you like your feeding position. So it's a feeding position or a position in a food chain or a food web. Your level in the food chain or food web. The word troph literally means feeder. So like an autotroph is a self-feeder. A heterotroph has to feed on something different at itself. And then the second mark, krill, is in the second trophic level, or you could say toothed whales are in the 5th or anything, but you need to say their trophic level. That was 11. 12, what is meant? Oh, the arrows. What do they represent? This question is always a very specific answer. What do the arrows show? They show the direction of energy transfer. You can't say who eats who or what eats what. They show the direction of energy transfer. And another way to say this, and you need it because it's 2 marks, you only have 2 options, is showing the direction of biomass, like living tissue, where that living tissue is going. If I were, what was that noise? I don't even know. If I were to be eaten by a shark, the biomass it will not get from me is the energy I put into making my bones. Shark can't digest bones. I don't think they can digest hair, so it's going to eat my hair, but that's going to come back out. Same thing like with cats. So the everything else it's able to digest would be biomass, like living material that will help like aid to the shark's body and give the shark an organic source, like organic material. Think about like a cow. A cow grazes, eats a bunch of grass, and within that grass that it eats, it creates fur, it grows itself, it makes, it grows bone, there's a lot that it does. So when we are eating a cow, we're not getting all of its energy. There's so many parts that we're not eating. We're not getting all of its biomass. Even if we tried to swallow cow bones, we would not get any energy out of it. We don't have enzymes that break that down. We can't eat their fur and get energy from it. We can't. So biomass kind of is like dependent on what kind of organism you are. Vultures can digest bone. We can digest bone. So that's like what biomass is. Bio means life. Mass is like the stuff that you have. So like your living tissue. In 40? Okay. Okay. Definition of a producer. It's an organism that can create or synthesize. Synthesize means to make. Photosynthesis, chemosynthesis. They can synthesize or create organic material or glucose, or you can call it carbohydrates, for the rest of the food chain. And this is the command word was explain the meaning of. Give one example of the marine environment. So if you reference that they do this through chemo or photosynthesis, you get another mark, like how they produce. And then an example could be phytoplankton, kelp, algae, zooxanthellae, chemosynthetic bacteria that live in hydrothermal vents through chemosynthesis. And that is going to be it for learning outcome C. Our next one is going to be learning outcome D, and we're going to start with number 9. Okay, and I'm going to pause it and pick it back up. Okay, so we're doing learning outcome D. Explain how populations of predator and prey are interrelated. And we're going to look at number 9 first, which is actually a little bit of a complex question. The question is, in some parts of the world, some areas of kelp are harvested by humans. Suggest, so give a reason for, and then explain how, so then give a reason why this could affect the population of crabs. So just anytime you're talking about numbers and it's saying suggest how it could change, there's only 3 options. It's going to increase, it's going to decrease, or it's going to stay the same. So there's your suggestion, and then your reasoning why you're saying that is the explain how. So how could it affect the population of crabs? So I'm going to go back to this page here. I even drew it out for you. I'm really visual, so I do draw a lot of things out. So here's our kelp, and they want to see the effect on crabs. So kelp gets fed on or organisms that eat the kelp. You have small fish, sea urchins, which will destroy them. That's what I did in blue there. And small fish are also in blue. Sea snails, there's the snails on the kelp. All of those will feed off of the kelp. Where the crabs come in is the crabs feed on small fish. And so if the kelp is gone, the small fish will lose a food source and their population will fall. Crabs will be living. They live on the bottom of the ocean or the bottom of the seafloor. So imagine the kelp is also going to be like a good protector for it. The crabs also eat snails that feed off of the kelp. And what else? And the crabs eat the sea stars that eat the sea urchins that eat the kelp. Okay. So the reason is there's going to be a fall in the population of crabs. So the crab population is going to decrease, and then you're reasoning why. If they are losing the sea star, small fish, and sea snail food, they're going to have to take over somewhere else. They're going to have to start eating something else, and that'll cause some competition. So why? You need to have, there's a fall in the population of crabs. Reason why, because there's less of a food source for them. There's less small fish, sea snails, sea urchins, sea stars, because they feed off the kelp. So that's obviously going to go away. Or you could say there's a fall in the population of crabs because there's less photosynthesis and there's less energy passed up the food chain. There's a fall in the population of crabs because there's less crab hiding places or habitats because they live within the kelp. Therefore, there's more predation on crabs because they can't hide. Or there's a fall in population of crabs, and then it's because you have less sea urchins or sea stars for the sea otters. Therefore, there's more predation on crabs. So sea otters will eat crabs. They also eat sea stars, and they also eat sea urchins. Well, sea urchins and sea stars are going to go away because the sea urchins feed off the kelp. Kelp's gone. So sea urchins are going to start to die out, and then the sea stars aren't going to have their main food source, which is going to be sea urchins. I know they also eat sea snails, but the sea otters are going to lose a food source on sea stars and sea urchins, so they're going to have to overcompensate somewhere else. They're going to have to eat more large fish, more octopus, and more crabs. But this question said, how's it going to affect the population of crabs? So that could be another reason, is that the sea otters are going to have to eat more of a different food source. Oh no. Here come the yawning. The yawns. All right. 13. Suggest why there's 2 arrows between the squid and the fish. Okay, so this is going on the food web. So those arrows, there's not one type of fish species. There's not one type of squid species. There's multiple different species. And they're also in different ages. You don't know what age they are. You could have a colossal squid feeding on smaller fish. Or you could have a fish feeding on like pygmy squid. Like it depends on their species, and it depends on what age they are. An adult squid could like feed on fish larvae or like fish eggs. So even if that fish is going to be like a Goliath grouper later on, it doesn't matter. It matters on life stages, and it matters on species. So they can feed on each other, obviously not simultaneously, but it does depend on their species, what size they are, what life stage they're in. 38. Cool. With reference to an example from the ocean environment, marine environment, explain. Oh my gosh, I'm sorry. Oh man. Okay, explain how populations of predator and prey are interrelated. This literally is straight from your topic support guide. All right. So you need your example. So I said sharks and tuna. It's good to also identify which one's the predator and which one's the prey, because I know some questions you do get extra marks for that. So just to be in the habit of identifying who's who. So always the population of your predator has to be less than your prey, always. You can't have more sharks than you do fish. The prey biomass, again, that's not blood or bones. Biomass is going to be like the living tissue. That's the living portion we get energy from. I wrote that for you. It's not part of the answer. I wrote it for you. The prey biomass is larger than the predator. So essentially, these two things are almost the same thing. The prey biomass, again, has to, like, their total biomass that they can contribute needs to be more than the predator. There has to be more population of prey than predator. Oh my gosh. Oh man. And then there needs, I'm not even tired. I don't know why this is happening. And then there needs to, the biomass, like the tissue that if a predator eats can go to the next trophic level. There needs to be more of that as well. The prey availability is a limiting factor for predators. So that is an interrelation between them. It is a biotic factor, but it is a limiting factor because if we take away prey availability, the population of predator will fall. And so that's what a limiting factor is. A limiting factor is anything that if that is lacking, if it affects the population of your organisms, it's a limiting factor. If it's something that's in a limit in the ecosystem and it affects your population, it's a limiting factor. Something that's not a limiting factor in the ocean is water. Normally that would be a limiting factor for photosynthesis, but in the water, no, it's not. It's not a limiting factor. If the prey population increases, then there will be more food for the predator. Therefore, the predator population can increase. If the predator population increases, this will cause the prey population to go down because there's too many of them. Always referencing that there's a time lag for your predator and prey population to increase, decrease. It's not like sharks are like, hey, look at that. 3,000 babies were just born right there. Fish babies. Let's have 3,000, or, let's have 1,000. It doesn't happen. There's a time lag, especially for the predator to realize, like, there seems to be an abundance of food source. It's not as soon as the new prey are born. There's like a change in the environment, and they notice that there's more available. Also, when going to like a new area to hunt or prey, it takes time to like find a mate and then reproduce. It also will take time to like get yourself established in a new habitat, develop niches, and fall into that like like moving somewhere new. Okay, so there's a time lag, and I know there's a graph coming up, so I'll show you what I mean by that time lag. They just cannot be changing at the same. The predator either increases or decreases in response to the prey. So if the prey starts to increase, you might see like a couple months later, the predator is going to increase. When the prey starts to go down because there's too many predators, a few months later, it's not, sharks aren't, dude, you ate one too many of our prey items. I guess now I'm going to have to go die. Like they're not dying at the same rate. So there is a time lag on the graph. And then mentioning that the predator-prey relationship is cyclical. They keep each other in balance. One number controls the other, or one population controls the other. The prey population controls the predator, for sure. Because if there's not enough of a prey population, then the predators die. So that was 38. 48 is our next one. All right, tuna and predators are predators of small fish, like silver sprats. Oh my gosh, I'm so sorry. I don't know why I'm yawning so much. Explain how the population size of tuna and silver sprats are related. So really pretty much the same question, how predator and prey are related. And they're giving you the example. So as the number of silver sprats increase, there's more food available for the tuna. Therefore, the numbers of tuna can increase. If you drew out a graph showing this, you could get 1 mark. And yeah, there it is. So they control each other. 50. Okay, so here it is. So see the time lag. The prey is your blue line, or for you it's just dotted. The predator is the solid line. Notice the population size. The prey is always greater than the predator. You always have to have more food than your eaters. And look at like letter Y. You see there's a peak at your population size for prey. Where my cursor is, there's a peak in population for predator, but it lags. It's not after. It's in response to, or it's not during. It's in response to. It is after. Right in the beginning here at X, you see the population of prey starting to increase, but at X, we're like at a very low moment for the prey or the predator population. Reason why the prey population can start to increase is because your predator population is so low. There's nothing to eat them. Okay, it's Z. Your prey population is like at a plummet. And you don't see that happening until, where my cursor is over here, right before F on your predator. So that's that time lag. So this is number 50. With reference, describe and explain what's happening to the population of predator species. So between X and Y. So describe is what's happening and explain is the why it's happening. Between X and Y. So X and Y of the predator species. So they're starting to increase between X and Y. So population goes up. And why is this happening? Again, due to the increasing in the population of your prey. Same question, what's happening between Y and Z? So Y to Z, 2 things are happening. We are hitting a peak at our prey, and then the prey decrease. So it reaches a peak and then it falls. So you don't want to say it's just increasing. It's not. It's at its peak and then it falls. Why? Initially there's a large amount of food and then your prey population goes down. Reference the time lag between. Hold on. Okay, yeah, no, this is of the predators. What am I thinking? Sorry, I know. I was just reading off of the dotted line. Ignore that. Between Y and between Z. For my predator, the pink line, we have an increase, that's a peak, and then a decrease. And so the reason why that's happening is because initially, yeah, they did have a lot of a prey population, a lot of food, but then it started to go down. So again, that time lag, it's increasing, and then they start to go down because their food is going away. So initially there's a large amount, and then prey population goes down. You can reference the time lag. It's 51. Okay, 52, 53 altogether. 52 says at time F, and that's on this back page, sketch the predicted population size of the original predator and prey from time F onwards. It says a second predator species was introduced. So what you want to show is that both populations will decline. The prey population is going to decline because now it has something else feeding off of it. Your predator population is going to decline because it's going to have competition now with another predator. The second mark is going to come from having the lag. You need to include the time lag. So no matter what your prey population is doing, and it does need to go down, your predator population will also go down, but in response to it, not at the same time. All right, so new predator is there. Their population numbers they're not going to ever peak to where they were before. They are going to continue to go down. And notice that my peak here for my prey is right after time F, and my predator peak is a little bit further after that. That's typically what I look for whenever I'm like, okay, I have to make sure I show a time lag. I will just make sure my peaks are different, which will make everything else fall into line too. Okay, 53 and then 50, so the rest of these, 53 to 57. You see a prey species population was removed and introduced to a new habitat. So initially we have this lag phase. This is called a sigmoid growth curve or a logistic growth curve. Sigmoid because it makes this lazy S shape. You have your lag phase where like your population is just coming to a new place. Then you have your exponential phase where they're being able to take advantage of all the resources available, and there's a lot of reproduction, not a lot of competition. And then we start to slow down because you're running out of resources and you're running out of habitat, you're running out of mates. This would be your carrying capacity, the flat line. So suggests why there's a time lag in the population growth curve of the prey, because they need to find shelter, food, or mates. There's not a lot of, look at your population size. Your population size is low. So there's, even if everybody's reproducing immediately as soon as they get there, you don't have a large population to even reproduce. Think like rabbits, like you start with 2 rabbits. Those 2 can make 12. And now you have 14 rabbits. And now each of those can make more. Well, not each of them, only the females. But then it starts to explode. Initially, you still have such a small population. Even having any sort of reproduction is not going to have that big of a growth yet until you have many reproducing at once. You could also talk about there's a lag to stress from a habitat change. It's like environmental stress, emotional stress. At time M, a toxin was introduced. So sketch the predicted population growth curve. Easy one. It's gonna go down, right? A toxin is introduced, so it's not gonna help their population numbers. The way students get this wrong is they immediately flatline it. They don't show like a gradual decrease. They show like a boom, like a flat line down, which means literally like extinction of that population, immediate, and then it's also like hitting the bottom. It's flatlining, so there's 0 in the population. So that you don't want to think in absolutes, because that is a big absolute. That's saying over almost no time at all, there's boom, like an immediate flatline. You don't want to do that. And that's saying here's the toxin, and immediately your population goes down, like it's a bullet or something. You also don't want to bring this all the way down to the bottom, because then that's going to say every organism in that population dies. It's not a bomb, so don't like do that in absolutes. Okay, cool. And so 57 is gonna be my last one for predators, predator prey. Okay. This one can get confusing, so color coding is helpful. So we're looking at changes in the masses in thousands of tons of two species of marine fish, A and B, in the North Atlantic Ocean between 1970 and 2010. One of the species is a predator of the other. So immediately, we want to figure out who's the predator, who's the prey. I know that's question 57, but look at your values. They're not the same. You can do two different y-axes like this whenever your numbers are so drastically different from each other, yet you're comparing two things. We're comparing their like mass, like the amount of them. So on your left side of your y-axis, this number is like 100,000 tons, right? Because they said it's measured in thousands of tons. So 100,000 tons, 200,000 tons. If I compare it to the right side of my y-axis, numbers aren't the same. And it's also in thousands of tons. So 1,500,000 tons. That's actually 1.5 million. 3,000 tons. No, that's 3 million. So for like me writing it out, obviously you can see it with the decimal place values, but writing it out was a good visual for me to be like, no, there's so much more of species B. Species B must be my prey species because there's so much more of them. Now you look at this initially and you're like, obviously it's A, right? A is so high, like A is higher than anything. But it's not, because these numbers are not the same. What A is measured on is not what B is measured on. And that's because one's a predator, one's a prey, and your prey species have to have much more of them than you do your predator. So there is much more amount of species B than there is species A. So species A must be my predator, and B is my prey. I'll just answer 57 then, because I just did. So the reason species A has a lower total mass than prey, which is species B. You could talk about the time lag, or you could use data to show that the population's like an increasing or decreasing trend because of the other, like because of the predator, or the prey species changing. Okay, so if we're looking, if B is your prey species, B is the prey species. Here it's peaking at 1995. You don't see an increase yet in your predator species for 10 more years until 2005. It does take for some species, like for tuna, it takes years, like 8 years to hit sexual maturity. So before that, they might not even be a good food item because they'd be pretty small. That's good. Yes. Again, too, like if you look at A, where this is going down, your predator population, we'll just think, your predator population is going down. So that starts in 1985. 5 years later is where it registers on your prey population and they start to increase. And it's not that they're increasing more than they were. They're just not dying as often because they don't have as many predators around. They're not like, hey, now's a good time to start a fish family because we don't have many predator fish around. That's not the conversation they're having. They're just not being eaten. They're not gonna, they don't also say like, what's the point in having all these baby fish if they're just gonna die? Like the parents aren't doing that. They're just not dying. Okay. I need to do 56. Calculate the mean, which is average, decrease per year in the mass of species A between 1970 and 1995. Okay. So per year, they're giving you a 25-year time span So no matter what, you're going to want to get that down to how much is that per year. So the average decrease per year. So we know it's a decrease, and you do want to answer you want to respond with an answer that talks about a decrease. Can either be with the negative sign or literally saying decrease. So we're looking at species A, and this is between 1970 and 1995. So we're at my green lines. That's what we're looking at. So we also need to consider what scale we're at. So we go 300 to 400. So they must be counting by 20s. 320, 340, 360, 380, 400. So each line is counted by 20s. So in 1970, they're at 320,000 tons. 1,000 tons. Read your units. So there's 320. And then in 1995, they're at 200,000. So they're already telling you it's in a decline. It is in a decline. You can see them go down, and 200,000 is definitely less than 320,000. And then, 1995. You're reading right on the line. It's 200,000. And you'll just subtract them to find the difference. 120,000. And that's over 25 years. They want to know what the decrease is per year. So you take that number and divide by 25. They want to know per year, not in 25 years. So if you divide that out, you get 4,800 tons per year decrease. Make sure you include the word decrease or like a negative, because it's not increasing. And that's it for learning outcome C and D.